Collapse of the wave function and decoherence, how do they compare? The collapse of the wave function and decoherence are two distinct concepts in quantum mechanics, though they are often discussed together because they address the measurement problem and the transition from quantum to classical behavior. Here are the key differences. Collapse of the wave function. What it is. The collapse of the wave function refers to the process by which a quantum system's state, initially described as a superposition of multiple possibilities, appears to reduce to a single outcome upon measurement. For example, in the double-slit experiment, when you measure which slit the particle goes through, the wave function collapses to a state corresponding to a particle going through a specific slit. Interpretation. Collapse is often treated as a postulate in the Copenhagen interpretation of quantum mechanics. It is an instantaneous, non-unitary process, not described by Schrödinger's equation. It is viewed as a fundamental aspect of quantum measurement, but the mechanism or cause of collapse is not explicitly described within the theory. Role. It explains the selection of a definite outcome in a measurement, resolving the apparent indeterminacy of superpositions. Controversies. Some interpretations, like the many-worlds interpretation, deny the collapse entirely and suggest that all outcomes occur in different branches of the universe. Other interpretations, such as objective collapse theories, propose physical mechanisms for collapse. Decoherence. What it is. Decoherence describes the process by which a quantum system loses its quantum coherence, i.e., the ability to exhibit interference effects, due to interactions with its environment. This occurs when the system becomes entangled with the environment, effectively spreading the quantum information into the environment and making the superposition states no longer observable. Interpretation. Decoherence is not a collapse but rather a loss of observable interference. The system still evolves according to quantum mechanics, but from the perspective of any observer, it appears classical. It provides a mechanism for the apparent transition from quantum to classical behavior without invoking a fundamental collapse. Role. Decoherence explains why superpositions seem to vanish in macroscopic systems or systems strongly coupled to their environment. It clarifies why classical probabilities emerge in large systems but does not select a single outcome, as collapse does. Key feature. Decoherence is a natural, unitary, and deterministic process governed by quantum mechanics. It depends on the system-environment interaction and timescale. Key differences. Relationship between the two. Decoherence can explain why quantum systems appear classical, why we don't see superpositions of macroscopic objects, but it does not explain how or why a single outcome is observed. Collapse is invoked to describe the emergence of a definite outcome in a measurement. Some interpretations argue that decoherence removes the need for collapse, while others see them as complementary concepts addressing different aspects of the measurement problem.